Let's start chapter 7, linear regression. In this chapter, we learn how to predict one variable using another. Regression is one of the most common and powerful tools in statistics. By the end of this topic, you will understand what a regression model is, how to evaluate it, and how to run it using R. We will also talk about how to interpret the regression in a meaningful way. The aim of this chapter is quite straightforward. First, we review what regression analysis does. Second, we learn how to evaluate a regression model, how good or bad it is. We will discuss the three key components: total sum of squares, model sum of squares, and residual sum of squares. Next, we will move to two important measures, the F value and R squared value. Finally, we will check how to run regression in R and how to interpret the output. In short, we will learn how to tell whether a model fits data well. So what exactly is regression? The goal is simple. We want to predict one variable y from another variable x. We assume that there is a linear relationship between them. The model looks like this. Here, y equals beta 0 plus beta 1x plus epsilon, where epsilon is unexpected noise, the random noise. And here beta 1 shows how much y changes when x increases by 1 unit, and beta 0 tells us what y would be when x equals 0. Why do we start with a straight line is here? Because it's the simplest possible model, easy to estimate and easy to interpret, and the term regression actually comes from the idea that outcomes tend to regress to the mean, regress to the return towards the population average. That is the idea of the regression. Okay, next, factors, the explanation for each part. Y equals b0. b0 is the beta 0 plus bjxj. b equals beta plus epsilon. B is estimator or coefficient. B is a regression coefficient for the predictor x. It shows both the direction and the strength of the relationship, whether y increases or decreases as x increases. And remember, B is an estimate based on our sample, only our sample, and not necessarily the true population value. Beta is not always the parameter. Parameter means the population's value. Beta is only the sample value. So if the assumption is violated, this is the beta is not parameter, only the biased estimator. And beta 0 is the intercept, meaning the value of y when x equals 0. Graphically, it's where the regression line crosses the y-axis. And finally, epsilon is the error term. This is a theoretical error and it's different from the residuals. Okay, next, let's see when OLS is unbiased and when can we use the regressions. There are four key assumptions. First is linear in parameters. The model is linear in the betas. The model is like this. Y equals beta 0 plus beta 1 x1 plus blah 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 plus epsilon. You can include squares or logs of x, but it is still linear in the beta. Beta is never logs or squares. That is a linear in parameters. Next is random independent data. Observations are correctly observations are collected fairly and are roughly independent. And third is no perfect multicollinearity. No regressors is an exact combination of others. Each adds new informations. Perfectly same values. We cannot add perfectly same x1 and x2 at the same time because we cannot estimate beta 1 and beta 2. And final point is the zero conditional mean. It calls exogeneity. The error does not move with the regressors. It can be written as like this: E epsilon conditionally x equals 0. The expected value of the error term given x equals 0. The mean of u conditional on x is 0. Practically, we need to avoid omitted key variables and check there are no reverse causality and no bad measurement error in x. This both assumptions is most important and is the most difficult point of the OLS assumptions, because this relationship is very difficult to be satisfied. But if the estimator is biased, is this case. Bias means our estimator misses the true target on average. Even if we collect more data, a systematic gap remains. More samples will not fix it. Formally, bias can be written like this: biased equals E beta hat minus beta equals not 0, then that is biased. This estimator is biased. Common causes is like the omitted variable, reverse causality, and measurement error, and so on. Unbiasedness is aiming the center, not about the spreading of the dataset. If the estimator is unbiased, then if the data is high variance, then it's okay, because if we has a lot of the sample size is large, then the standard error falls like 1 divided by root n. But if we has biased, the estimator is with bias, then increase n does not reduce the errors systematic part. So this is very problematic. Even if we gather many n sample size, but the estimator is biased and there is a gap between the true parameter, population's value and sample value is different. So we need to check these assumptions first. This is very important point of the OLS regression. And next, under the 5 assumptions, 1, 2, 3, 4, and 5, homoscedasticity is also satisfied, then OLS is blue, best, linear, unbiased, and efficient. This step we add one more assumptions. In that case, the OLS is the best estimation. The extra assumption is homoscedasticity, and the error variance is the same for all x. We can write like this: always the same standard error with linearity, random, no perfect multicollinearity, zero conditional mean, no exogeneity or no endogeneity, and homoscedasticity or constant variance. Then OLS is the best linear unbiased estimator. This is called Gauss-Markov theorem. Best linear unbiased and efficient, not the, I think the best linear unbiased estimator is blue. Okay, next is the graphical explanation. Here we can see the how intercept and gradient works in a graph. The graph beta 0 is where the lines start here. The baseline value of y when x equals 0. The gradient or slope is beta I. That tells us how steep the line is. And on the left graph, we have the same intercept but different gradient. The line tilts differently. On the right, the gradient are the same but the intercepts are different. So the lines are parallel. When you read the regression result, always remember the slope shows how much y changes with x. Slope is how much y changes. And the intercept tells you where the line hits the y-axis. These are the intercept. So now we move to the how the regression line is actually calculated. This is called the method of least squares. The idea is simple. We drew a line that makes the difference between observation data point and the line as small as possible. Minimize the error between y and the fitted line. That is the idea of OLS or simple regression. The distance is the issues, and the distance of sample y and fitted value y is very important. The distance of the x-axis distance is not problem, not the aim of this in this case. These vertical gaps are called residuals, and they are the errors between what we observe and what the model predict. Model prediction is blue line, and the real dataset is blue point, and the gap is residuals. Now that we know that what the residuals are, and next question is, how do we measure the total error in the model? We can't just add up the residuals directly because some of them are positive and some of them are negative. So they would be cancelled out. So instead we firstly squared and we sum them. That total is called the residual sum of squares. It's SSR. The SSR tells us how far our predicted values are from the actual dataset. A smaller SSR means the regression line fits the data more closely. So minimizing this number is what the least squares method does. Least square means to minimize these squared residuals. Then this is the OLS. This is called OLS. Okay, next, let's look at the how well the model fits the dataset. We use something called R squares, written as like this. R squares tells us what proportion of the total variation in y can be explained by the model. It's calculated using three kinds of sum of squares: SST, and SSR, and SSM. SST is the total sum of squares, showing how much y varies from its mean. The red line is mean, and the difference. SSR is residual sum of squares, the unexpected part. And SSM is the model sum of squares, the part explained by the regressions. SSR is residual sum of residuals, sum of squared residuals. This is the sum of squared residuals, and the compared with the only mean. Compared with the mean is SST, compared with the fitted line is SSR, and this is the model sum of squares, how much better the fitted line is compared with just taking mean. And finally, we get the R square equals SSM divided by SST, or equivalently 1 minus SSR divided by SST. The closer R square is to 1, the better the model explains the dataset. Also, in simple regression, the square root of R square equals the Pearson correlation coefficient R. So R square gives us a numerical sum of how well our line fits. Okay, this figure shows the SSR, SST, SSM again. SST is total sum of squares. SSR, residual sum of squares. SSM, model sum of squares. And relationship is here. The distance from the fitted line and real dataset, SSR, fitted line and model, fitted line and the mean is SSM, and total is SST. SST equals SSM plus SSR. If our model fits very well, the residual part SSR becomes small and the model fit part SSM becomes large. That's why we say a good model explains most of a total variation in Y. Okay, next, now we test how good the model is. First, we turn sum of squares into mean squares by dividing by their degree of freedom. Here, MSM, model mean square, is SSM divided by the number of predictors, P. P is the number of predictors. And next is MSR, residual mean square. This is the SSM divided by N minus P minus 1. N is the sample size, P is the number of predictors, and minus 1. Okay, P forms the F ratio. F is the MSM divided by MSR. If F is large, the model explains a lot more variance than the noise. But remember, the statistical significance depends on the degree of freedom and the chosen alpha level, not just on the F being above 1. Rule of thumb of here, larger F suggests a better model, but this is also depend on the degree of freedom, so please check. Next is F-test. Does the model explain more than taking just an average? A statistical test that evaluates a hypothesis using the F ratio and the F distribution. Null hypothesis is here. The model does not explain more variance than the mean. Alternative hypothesis H1 is the model does explain more variance. If the F ratio is statistically significant, we can reject H0, the null hypothesis. That means the regression line fits the data better than the intercept-only model that uses just the average. That is the meaning of f-test in simple regression case. Next, in the multiple regression case, the f-test can be used to assess the differences among group means or to compare with the models. The f ratio is here, MSM divided by MSR, and between group divided by within group. ANOVA context, null hypothesis is here, all group means are equal. And alternative hypothesis is here, at least one group means is different. This test is the f-test in ANOVA context. And regression context, the regression context is here. A f-test can compare two models. For example, model 1 with 2 predictors versus model 2 with 3 predictors. We can compare the model 1 which includes the 2 predictors, 2 x1 and x2, and model 2 has the x1, x3, x2, x3. We compare the result, and which model is better we can check. If the test is significant, model 2 provides a statistically significant improvement over model 1. So we can adopt the second model, model 2. Next is the t-test. T-test is the variable different from 0 or not. That is the t-test. Null hypothesis is here, the parameter equals 0. And alternative hypothesis is here, the parameter is not 0 in two-sided case, or greater or less than 0. It is one-sided case. In regression, the formula is here, t equals b observed minus b expected divided by standard errors. It follows the t distribution with the appropriate degree of freedom. In short, the t-test asks is the effect distinguishable from 0. That is the t-test. Okay, so the next, we will move on to the practice session of R. Here is a dataset of 200 albums, and the outcome Y is sales. Sorry, this is Japanese. The outcome variable 非説明変数 is sales. Predictor variable 説明変数 or independent variable is the amount of spent promoting the album. This is, for example, the adverts for sales. Okay, first we will move the simple regressions. And first we load the dataset. First step, load the dataset and use LM to fit the model. And call summary to see the output. Okay, let me check the result. This is the chapter 7 code. I checked all the code, so I think it works well. Firstly, we set the working directory, and if the environment is there is a lot of dataset in the environment, we can clear all dataset in our environment, running like this. But we turn off this command. This means the language is English, because my computer is Japanese one, so the language should be in English. And run the command to access the album 1 dataset. Read the dataset album sales 1 dot and the data. So we find the dataset this, and also we can set album 1 Then we can check like this. AdWords, sales, only two variables. Okay, and we can use this dataset in our environment. So next, run the simple linear regression. In simple linear regression, we use LM command. LM means sky blue part is linear regression. It means linear regression, LM, linear model. And explained variable is here, and explanatory variable is here. This is dependent variable. Dependent variable first, and predictor or independent variable second. Advert, green part, and we designate the dataset. Data equal urban1. Designate data. Okay, we run the command. Then we want to check the summary of result or summary of the result. Then command summary and regression name. Then we can see the result like this. I lost the command. Okay. I would like to check the result from the slide. Sorry, this is the Japanese. This is the how to check the result in English. This is a command for LM formula equals sales. Independent variable is advert and dependent variable is sales and data is urban1. This is the meaning of command, and this is a residuals. Residuals are the gap between observed and predicted values. The part the model cannot explain is here. And green part is coefficient. Coefficient tells us direction and size of the effect. Size is here. Estimate includes the size. This is a standard error, and this is the p-value. So we can check the statistical significance here. Sign gives directions, magnitude gives the effect size per 1 unit change in the predictor. Interpret with its SETP value and GI, confidence interval. In this case, the p-value is smaller than the very close to 0, so that it is statistically significant. Okay, next slide is also explain the coefficient. This estimate is magnitude of each estimator, and standard error, magnitude of error for each estimator. And t-value and p-value is here. T-value is used for t-test, and the result is p-value. The p-value is very close to 0, and this stars, 3 stars means here 0.001 level significant. This is a graph, and this green range is here, intercept is here, and slope, this how to say, this color's slope is the advert, and this blue line is the fitted line. Statistically significant at the 5% level means the p-value is smaller than 0.05. In this case, statistically significant at the 0.001 level. So 0.1% level, I think. This 0.05 cutoff is a common convention in introductory statistics, but however, it is not an absolute standard. Please note that. Prefer to report the exact p-value and the 95% confidence intervals, and also please show the effect size and practical importance. That is important point. Firstly, we can check the statistically significant or not, but in actually the effect size is also important. And only check the 5 lower than 5% or upper than 5% is not good behavior for the statisticians. It is just one indicator, not a absolute standard. Okay, next is the other explain for the other part. This is the residual standard errors and degree of freedom, R squared and adjusted R squared and F statistics. Next slide, there is the detailed explanations. Residuals, each y minus y hat, we judge fit by the residual variance and residual standard error, not the mean residual. Red area is the degree of freedom, n minus k minus 1. Infinite sample for the t distribution. T-test can be done. If sample size is larger, then more powers. And this is the R square, proportion of variance explained. In simple regression, R square is here, like this. Pearson's R is squared, Pearson's R is R square. And this purple area is the adjusted R square value. This is penalty. There is a penalty that the extra predictors and is often preferred than simple R square. R square is increasing if we use a lot of explanatory variables, but in adjusted R square case, there is a penalty if we use a lot of predictors. So basically the adjusted R square would be preferred. And this is the F statistics, F value and F test result. Test the model vs intercept only case, that is the F test. So the most part of output of summary in R can be read. Okay, next step, some textbooks often report the VIF, especially the especially the some books often report the VIF, variance inflation factors, to check the multicollinearity. VIF can be calculated 1 divided 1 minus R2, where R2 is from regressing the predictor X on the other predictors. However, VIF thresholds are heuristic and do not use VIF mechanically to pick variables. I think that many researchers, economical researchers or statisticians, do not use the VIF for the statistical analysis. So you do not have to check the VIF in the multicollinearity problem. Checking simple correlation is fine for a quick screen, and thinking carefully about the causal identification matters more. The causality is matters today, and VIF is not very big issues today. Also in R, the car packages provide a VIF, but it can conflict with the other packages. So in this course, we will skip the VIF and focus on the modeling choice that reflect the causal questions. That would be better, I think. Okay, next. in the simple regression, R square equals the square of the Pearson's correlation R. So if you take the square root of R, then you square root of R square, you can get the magnitude of correlations. Okay, then command is here. Square root of this is the there is the R square. R square is here. R square is here. So if we calculate the square root of 1, then we can get the Pearson's correlation R in the simple regression case. This one. And next, let's expand the predictor to several cases. We fit 2 models. Sales, this is the independent variable. This is a dependent variable, and this is only one independent variable. Next, urban sales 3 case. This is the dependent variables, and independent variables are 3. Advert, airplay, and attract. Data is same, and we can check the summary, and we can compare with them. Next, I would like to use the album 2 dataset. This imports album 2 dataset, and this is the simple regression. Second is a multi explanatory variables regression, and check result by summary. First summary is here. This is the 1 predictor case, and this is a 3 predictor case. We can focus on the 3 predictor case here. It's just added 2 explanatory variables, advert plus airplay plus attract. Formula is sales tilde advert plus airplay plus attract. We can add the new explanatory variable by using plus. The idea is very simple. By adding relevant predictors, we may explain more of the variation in sales. In a moment, we will compare this model with the simpler one to see if it actually improves. And this is a quotient. Each row shows an estimated effect for the predictor with its standard error and t-value and p-value. The asterisks are same. Asterisk indicates the statistical significance. And in this case, the adverts and airplay is the all of them are statistically significant in the 0.1% level. And this is the result. Sales in the week after release is influenced by adverts, airplay, and attract. So next, we would like to check the impact of these 3 explanatory variables. It looks like the magnitude is the estimate. So the estimate column, then the attract is the biggest value, 11, about 11. The airplane is 3.3 and advert is 0.08. So the magnitude of value is biggest in attract. Attract is the biggest. Attract has the biggest impact on the sales. But we need to check the units of these variables. the predictor on different scales. Please check, and please be careful. A large coefficient might reflect the unit rather than a true large effect. To make fair comparisons, we often need to standardize the predictors. That way, each coefficient represents the effect of one standard deviation change that makes size directly comparable. In this case, attract looks the bigger impact, but the scales attract is small and sales is big, so we need to standardize. And standardized data is here. We can scale command. We can use scale command. This code creates a new data frame with mean equals 0 and variance equals 1 for each variable. Album2 scaled is the data frame parenthesis sales equals scale album2 dollar sales. Adverts equals scale adverts. Airplay equals scale airplay. Attracts equals scale attract. Then the data should be standardized. And this is the result. The dataset is standardized. Variance equals 1 and mean equals 0. Okay, we can check the result by R interface. Standardized command is here. This. Then the scaled new dataset is here. Then we can check, for example, head album 2 scale and run. Then we can check the, yes, this is the around 0. This is totally different from the head album 2. Not scaled version is here. Is different. And random multiple regression using the scales dataset. LM command we use and others are almost same. Only the change is data is album 2 scales. Sales tilde advert play plus airplay plus attract. Then we run one and check the result here. Then we get this result. Okay, we can check it in slide like this. This is the not scaled version, and this is the scaled. This is after standardized version. Yellow-green numbers are the same. I mean the t-value and p-value statistical significance are all totally same. And R squared and other indicators are totally same. Totally the same. But red enclosed area is different. So the magnitude can be different, differ only in the absolute magnitude of the values surrounded by red. And this will make it easier to compare the size of the impact. In the original data case, estimate of attract is biggest. So attract is very important for sales, but in the result, attract is not has the big impact in the standardized case. And adverts and airplays is almost the same and the 2.5 bigger impact than attract. That is a result. And in your dataset, the scale is very different. You can try standardize. Okay, next step. We can also check the confidence intervals. Confidence intervals are obtained with conf int command. We can get the data set. This is 2.5% to 97.5% range. And finally, the comparing regression result ANOVA command. This run an F-test for nested model. Okay, we can check over run. Then we can get the result like this, ANOVA command. And the result is here. We can compare the RSS model 1 and model 2. RSS is residual. You will also see the model 2 has a larger RSS and model 3 is smaller RSS. So in this case, model 1 and 2. RSS is smaller in model 2, model 2. Then the model 2 is better than model 1 in this case. So add airplay and attract is better than the simple regressions. That is the conclusion. Prefer below model in this stars level 0.1 lower than 0.1 percentage significant level. Next is the create figure from regression result. We can check the normality, extract residuals and make quick diagnostic plot. Histogram plus normal curve. We can check the residuals by using this command. The meaning is here. This is the predicted fitted value and this is the model residuals and this is a geom smooth. This is a linear line. Add a linear regression line. If this line is approximately horizontal, the residual shows no systematic pattern. That means the assumptions of independence and homogeneity are likely satisfied. We check the result. We check the OS is okay or not by using like this. We check residuals are normal distribution or not. And residuals are normal distribution, then it is okay in some case. And this is the result. I also make the command. And this is the residual density and this is the studentized residual distribution. And next is the fitted line. Fitted line is horizontal, so there is no specific relationship. So textbook says it seems to be acceptable. Okay, this is the OLS. And basically the important point is the LM. Using LM command is very important. And I would like to skip the robust regression bootstrapping. Bootstrapping is the resampling again and again method. But I would like to skip the bootstrapping content because and you do not need to use it for the assignment. If you already have experience with R or doing statistical analysis, you may use it freely, of course. So please refer to the provided code and provided slide. A lot of samples generate a large number of resampling is the bootstrap method. If your sample size is very small, then you can apply this method. Sometimes it is recommended, but it is a bit complex, so I will skip. And finally, I would like to explain the dummy variables. Okay, this data set, okay, the festival dataset we use, and our dataset has a variable music with value like crusty, metal, and indie kit. And we create these dummy variables. We want to create these dummy variables to use these in regressions. In this command, we can create the dummy variables of crusty and metal and indie kit. Dummy variable means if the participant is in this case the participant likes crusty, then it is 1 and otherwise 0. Like participant like no crusty and participant are metal, then I'm not sure metal and crusty and indicate me exactly means, but the E or C is metal, then 1 and otherwise 0, indicates 1, otherwise 0. Such kind of 1 or 0 variable is the dummy variables. And we can use such kind of dummy variables as the explanatory variables. In other case, for example, if female, then the dummy variable is 1, otherwise 0. If the Japanese, dummy variables 1, otherwise 0. If the old man, if the age is over 65, 1, otherwise 0. Such kind of the dummy variables can be seen. And we can use the dummy variables in your regression. When crusty equals true, otherwise false. Metal true, otherwise false. Indicate true, otherwise false. We often use dummy variables. Dummy variables setting is the, for example, you focusing on the female income, then female would be the dummy variables. Then we can easily read the result. For example, in other case, you focusing on some, for example, some race or some profession or something, then we can set the dummy variables. And if there is a significant effect, then we can discuss about that. For example, in Japan, females' income is unfortunately lower than male. That is a discussion point. Okay, we can use the R to conduct dummy variable analysis. This is a dataset. Please check R code. Create 3 dummy variables: crusty, metal, indicate. And after that, create a regression model. We check the dataset like this. And this is the crusty dummy variable. Metal is metal dummy variable. Indicate is indicate dummy variable. This is the regression LM. This is the explained or dependent variable. This is the explanatory variables and summary. This is the result. This is the effect of dummy variables. It is same as the slide. To summarize, turn categories into dummies and leave one category out as the reference group. Interpret each dummy's coefficient as different from the reference. In this case, class T versus others, Metara versus others, Indies versus others, female versus others, US versus others. This is how we include qualitative information like group or type in a linear regression model. For example, we cannot change Metaras to the continuous variable, so we use dummy variable. This is all the content of the regression, chapter 7. Thank you very much for listening.